Welcome to this explainer. Today, we're looking way past that standard poster hanging in every high school science classroom. We're going to look at the periodic table of elements for what it truly is, the ultimate multi-generational jigsaw puzzle of the universe. Honestly, it's accurately referred to as the symbol of chemistry for a reason. And the story of how it was pieced together, it's easily one of the greatest detective stories in human history.
So how do you even organize the building blocks of the entire universe? Imagine somebody hands you a huge pile of puzzle pieces, but you have no box. You don't know what the final picture is supposed to look like, and you have literally no idea how many pieces are missing. That was the reality for early humanity. Prehistoric humans actually knew about a handful of elements, right? They had discovered things like gold, silver, iron, phosphorus, sulfur, zinc, arsenic. But these were totally disconnected pieces. They understood what a chunk of gold was, sure, but they had absolutely no idea how these fundamental building blocks fit together on a cosmic scale. Where do you even begin? Well, to answer that, we're going to track the brilliant minds who slowly cracked the code. We'll move from the 18th century with Lavoisier through to 1829 with Dobereiner, hit the 1864 breakthroughs from Newlands and Meyer, look at Mendeleev's genius in 1869, and finally reach Moseley in 1913. Okay, let's dive into this. Section 1. Early sorting and triads. Our story officially kicks off in the 18th century. Antoine Lavoisier made the very first, basic, but absolutely essential classification. He sorted the known elements into two simple buckets, metals and nonmetals. Then the plot thickens in 1829. A German chemist named Johann Dobereiner started looking a little closer at these pieces, and he noticed something fascinating. He found that certain elements naturally grouped together in threes, which he called triads. These triads shared very similar chemical properties. Dobereiner had effectively found the first true edge pieces of our puzzle, realizing that these elements weren't just random. And this brilliantly illustrates his big aha moment. Take a look at one of Dobereiner's classic triads: lithium, sodium, and potassium. Now they act similarly in the real world, but check out their atomic weights. Lithium is 7, potassium is 39. If you add those together, you get 46. Divide that by 2 to find the average, and you get exactly 23. Which just happens to be the precise atomic weight of the middle element, sodium. It was a stunning hint that a deep mathematical order governed the universe.
Moving right along to Section 2, Finding Rhythm and Curves. Fast forward to 1864, a period of really rapid discovery where two different scientists were working on the exact same puzzle from totally different angles.
On one side, we have the English chemist John Newlands. He took the 62 elements known at the time, arranged them by increasing atomic mass, and he found a repeating rhythm. He proposed the rule of 8, basically noting that every eighth element closely resembled the first one in its properties, kind of like octaves on a piano. On the flip side, in that very same year, Meyer was looking at things visually. He plotted a graph of atomic weights against atomic volumes, and his famous curves physically demonstrated the exact same periodicity. We had rhythm and we had physical curves. The momentum was building.
Which brings us to Section 3, Mendeleev, the master organizer. In 1869, Russian chemist Dmitry Mendeleev steps up, and he is widely considered the true father of the periodic table. At this point in history, humanity had discovered exactly 63 distinct elements. Mendeleev took all 63 of these puzzle pieces and systematically arranged them by increasing atomic mass, carefully aligning those with similar properties into vertical columns.
Now, what's really interesting about this is the sheer audacity of Mendeleev's genius. Most scientists back then would just try to force those 63 known pieces to fit together, even if the picture ended up looking a little warped. But not Mendeleev. When his pattern dictated that an element should be there, but he didn't have a known element to put in that spot, he simply left a blank gap in his beautiful table.
And he didn't just leave gaps. He boldly predicted the atomic mass and the specific chemical properties of the elements that would eventually fill those spaces. He essentially told the scientific community, hey, go out and find this exact puzzle piece because I know what it looks like. And the craziest part, when these elements were actually found years later, his predictions were incredibly accurate. I mean, this is really the emotional peak of our detective story. Mendeleev had practically read the mind of the universe.
Let's move to Section 4 and see how this builds to the climax, Moseley's final atomic code. Because as brilliant as Mendeleev was, his table still had a few frustrating flaws and discrepancies. The puzzle was 99% complete, but a few pieces were jammed into the wrong spots.
To understand the ultimate fix, we just need to clearly define two terms. Up until now, everyone was sorting by atomic mass, which is essentially just the weight of the atom. But there's another property, atomic number. And this isn't about weight, it is the exact specific number of protons located inside the nucleus of an atom.
Enter our final hero. In 1913, a scientist named H.G.J. Moseley. Moseley arrived with a massive plot twist. He used high-tech X-ray emission to look inside the atoms and determine their exact atomic numbers. The massive twist was this: we had actually been sorting the puzzle by the wrong numbers the entire time. Weight was a good guess, sure, but proton count? That was the absolute truth.
So the crucial point is how Moseley applied this. By measuring those X-ray emissions, he mapped the exact atomic number for the known elements. And when he took Mendeleev's table and rearranged it by increasing atomic number instead of atomic mass, it was literally like magic. Every single flaw, every frustrating little discrepancy in Mendeleev's arrangement just vanished. The pieces snapped together perfectly. This breakthrough allowed Moseley to modify the periodic law itself. The modern law basically states that the physical and chemical properties of elements are periodic functions of their atomic numbers, not their masses. And why does this matter? Because this final modification created the brilliant, unbreakable code that governs everything around us. The ultimate puzzle, centuries in the making, was finally structurally complete. And that brings us to today. Because of the incredible, multi-generational foundational work of Lavoisier, Dobereiner, Newlands, Meyer, Mendeleev, and Moseley, we now have a modern periodic table containing 118 elements. All 118 are perfectly organized into a tabular form.
But, science never truly stops. This table isn't just some historical artifact. It's a living tool that helps us understand electronic configurations, chemical reactivity, and the very nature of matter. So what does this all mean for the future? With 118 elements now perfectly organized, what hidden patterns, undiscovered technologies, or new understandings of the universe will the periodic table help us unlock next? Thank you so much for exploring this fascinating journey with me on This Explainer. Keep asking questions and keep looking for those patterns.